Hello again. Today we're looking at section 4.1, which is going to be inverse functions. First we'll talk about one-to-one functions. Then we'll talk about what an inverse function is and how to show that two functions are inverses. And then we'll talk about how to find an inverse function and what the graph of two inverse functions looks like. Let's get started. First of all, what do we mean when we say inverse function? Well, an inverse function is created by exchanging the x's and y's of the original function. So an inverse function basically makes a function run backwards. Not every function has an inverse function. In order to have an inverse function, the original function must be one-to-one. So now what do we mean by one-to-one? Now before I tell you what one-to-one means, let's remember what the definition of function is anyway. Here I have a set of ordered pairs, -2, 2, -1, 1, 0, 0, 1, 3, and 2, 5. F is a function because each x value matches only one y value. The x value -2 only matches +2. It doesn't get reused anywhere else. The x value -1 only matches a y value of +1. That x value doesn't get reused anywhere else. Now f is considered one-to-one because it is a function in which each y value matches only one x value. So it's a function because each x matches only one y, but it's one-to-one because each y matches only one x. Notice the y value of 2 only matches an x value of -2. The y value of 0 only matches an x value of 0. You may have noticed previously when we first talked about functions that it's possible for the y values to repeat and still have a function. It's still possible for that to happen. However, now we're saying that there's a special type of function called a one-to-one function in which the y values do not repeat. Each y matches only one x. Now if we reverse the x's and y's, we get a different function that we'll call g. If you reverse the x's and y's here, you get 2, -2. If you reverse these x's and y's, you get 1, -1. So function g is considered the inverse function of f, and g is a function because f is one-to-one. Imagine if we had a function here where the y values got reused, then when you switch the x's and y's, the new relation would not be a function. So that's the importance of one-to-one. A function can only have an inverse function if it is a one-to-one function. You may recall back in chapter 2 we looked at this way of representing a function where we had the domain here and we matched each number in the domain to a number in the range. This was called mapping. And here it's kind of useful to be able to see whether a function is one-to-one this way. Here we can see that f is a function because each x value only matches one y value. Each x value only matches one y value. So this is a function. However, notice that for this y value, it traces back to two different x values. So it is a function, but it's not a one-to-one function. However, over here, the 1 matches a 5, and the 5 only matches a 1. The 3 matches a 6, and the 6 only matches the 3. The 2 matches a 7, and the 7 only matches a 2. And 4 and 8, and you can go back from 8 to 4. So this function is one-to-one. So to sum it up, a function is one-to-one if each x produces only one y, that's what makes it a function, and each y can be produced by only one x, that's what makes it one-to-one. Here we have example 1 and it says decide whether each function is one-to-one. So here is y equals -4x plus 12. Now each x that we plug in is only going to produce one y answer. And each y can only be produced by one particular x. So each x produces one y. Each y can only be produced by only one x, therefore this is a one-to-one function. But when we look at part B, we have square root of 25 minus x squared. Now, it's not the square root that's going to cause the problem, it's the square here. Each x that we plug in does only produce one y. If you plug in, say, 1 for x, that only will calculate one answer. If you plug in -2 for x, that only will calculate one answer. But each y can be produced by two different x's, because think about if we plugged in x equal to -2. If we did -2, then -2 squared would be 4, and 25 minus 4 is 21, so we get square root of 21. But if we plug in +2, we get the same thing, because -2 squared is 4, and +2 squared is also 4. So here are two different x values that are producing the same y value. That does not keep this from being a function, but it does keep it from being a one-to-one function. Now let's look at each of these together and see if we can tell whether each function is one-to-one. Okay, on this first one we have y equals -1 over x plus 2. Each x is only going to produce one y, that's what makes it a function, and each y can only be produced by a particular x. So this is going to be considered one-to-one. Now in part B, we have a squared binomial, and you'll recognize this type of function from section 3.1 when we graphed parabolas. In fact, this is quadratic, and it's going to graph a parabola whose vertex is at -2, -6. And this is not the only way to tell whether a function is one-to-one or not, but it is a very helpful way. And when I look at the graph of this parabola, I can see that it reuses almost all the y values, all of them in fact except the one at the vertex. So this is definitely not one-to-one. And now when we look at part C, the cube root of x plus 1 minus 3, I just want to remember what the cube root function looked like. Do you remember this from section 2.6? We talked about the cube root function, and it kind of looks like a cubic function turned on its side, sort of. And so you can tell by looking at this graph that the cube root function is one-to-one because none of the y's ever get reused. Each y value is only part of the graph one time. So this is a one-to-one function. This idea of using the graph to tell if a function is one-to-one brings us to what's called the horizontal line test. If a horizontal line can be drawn through a function so that it touches the graph twice, the function is not one-to-one. Here we have a semicircle, the top half of a circle, and you can tell that this graph would pass the vertical line test, so it is a function. However, it does not pass the horizontal line test because we can draw a horizontal line that cuts the graph twice. So it is a function, but it's not a one-to-one function. And the problem is that if a function is not one-to-one, its inverse graph would fail the vertical line test, because remember, in an inverse, all we're doing is switching the x's and y's. So if the function reuses y values, then its inverse will reuse x values, and the inverse will not be a function. Now, on example 2, it says determine whether each graph is the graph of a one-to-one function. Okay, well here we have a function that's curving, and when we draw a horizontal line, we are able to cut the graph more than one time. So this graph is not one-to-one. However, on part B, this is a straight line, and so when we draw a horizontal line, each horizontal line only can touch the line one time, and therefore this graph is one-to-one. So this is pretty easy. You can pause the video and determine whether each of these is one-to-one. And now I'll just go through it with you and check for you. On the first one, we draw a horizontal line, we cut the graph twice. This is not one-to-one. On the second one, any horizontal line will only touch the graph one time, so this is one-to-one. And the third one is one-to-one. I just want to point out to you that there is a way you can sometimes determine if a function is one-to-one without necessarily seeing its graph. Remember the function that we looked at in example 2b was this straight line that is decreasing on its entire domain. Well, if a function is always decreasing, it will never repeat y values. So if you know a function is always increasing or always decreasing, you can know by default that it's one-to-one. So for example, any straight line is automatically going to be one-to-one. Also, x to the third power would be one-to-one, and the square root of x would be one-to-one, because both of these are examples of functions that are increasing on their entire domain. Now that we are very familiar with one-to-one functions and what that means, let's start talking about inverse functions. So I have two functions here, f of x and g of x. And as an experiment, let's evaluate f of 4. So we're going to plug 4 into the f function. And f of 4 is equal to 37. Now let's plug 37 into the g function. So that will be 1/8 times 37 minus 5/8. That's 37/8 minus 5/8, which is 32/8, which reduces to 4. So when we plug 4 into the f function, we get 37. And when we plug 37 into the g function, we get 4. In other words, g reverses the effect of f. In fact, it doesn't just work for 4 and 37. For any values of x, if we plug a number into the g function and then plug that number into the f function, we'll get the original number back. And if we plug a value into the f function and then plug that answer into the g function, we'll get the original value back. Or using composition notation, you could write it this way. F compose g of x is equal to x, and g compose f of x is equal to x. So this brings us to the true definition of inverse functions. We said before that an inverse function reverses the x's and y's, and that is completely true. But here's the technical definition. If f is a one-to-one function, then g is the inverse function of f if f compose g of x equals x for every x in the domain of g, and g compose f of x equals x, and g compose f of x equals x for every x in the domain of f. Now there's no way that you could plug in every number in the domain of either one of these functions, so what we usually do is just compose with the x in place, and when we do the algebra, then we see that the composition reduces just to x, so we have to compose both ways to verify that two functions are inverses. And by the way, the condition that f must be a one-to-one function is necessary because if f is not one-to-one, then although g might be the inverse of f, it won't be a function. So we can't call it the inverse function because if f is not one-to-one, g will fail the vertical line test. So here in example 3, we're going to use the definition of inverses to determine whether f and g are inverse functions. So what we need to do is show that f of g of x reduces to x, and we also need to show that g of f of x reduces to x. We'll have to do both compositions, and if either one of them fails to reduce to x, then we'll say that f and g are not inverses. So first of all, f of g of x will actually be f of this function. So I'll be plugging cube root of x plus 1 into the f function. So instead of x to the third minus 1, it's going to be this expression to the third minus 1. Now the third root of the third power is just the first power of this expression under the radical. So we'll have x plus 1, and then this minus 1 will still be there. And when we combine the terms, we get x. Okay, now let's compose the other way. Let's do g compose f of x. And this time we'll be plugging the f function into the g function. So cube root of x plus 1 will become cube root of this expression plus 1. So cube root of the f function plus 1 reduces to cube root of x cubed, which is just x. So we see that f and g are inverses because when we find f compose g, it equals x, and when we find g compose f, it also equals x. Now here's one that you can practice on your own. you have two functions here, f of x equals 2x plus 4, and g of x equals 1/2 x minus 2. And we want to use the definition of inverses to determine whether f and g are inverse functions. So you'll need to find f compose g, and you'll also need to find g compose f. Pause the video and see if you can make it work, and see if both of these reduce to x. And if they do, we can say that they are inverses. Okay, now if you've had a chance to try that on your own, let's do it together. To see if these two functions are inverses, we'll first need to evaluate f compose g of x, which can be written as f of g of x, which tells us that we're going to plug the g function into the f function. So f of g of x becomes f of 1/2 x minus 2. So now f was 2x plus 4. So 2x plus 4 is now going to become 2 times this expression plus 4. So we'll have 2 times that expression plus 4. And now distributing the 2, we're going to have 2 over 2x minus 4 plus 4. The minus 4 and plus 4 will add up to 0, and the 2 over 2 will reduce to 1. So this way we reduce to 1x, which is what we wanted. And now let's compose the other direction. So we'll look at g of f of x, which is going to be g of 2x plus 4. Now we will plug the 2x plus 4 into the g function. So 1/2 x minus 2 is going to become 1/2 times 2x plus 4 minus 2. Now distribute the 1/2. And 2 over 2 reduces to 1. 4 over 2 reduces to 2. And the 2 minus 2 adds up to 0, so we end up with just x here. So since the composition both directions reduce to just x, we can say that f and g are inverse functions. Now there is a special notation used for inverse functions. If g is the inverse function of f, then g is written as what looks like f to the negative 1, but we pronounce it f inverse. In fact, that negative 1, although it's a superscript, is not an exponent, and f is not a base. So it looks like f to the negative 1, but we read it as f inverse. So for f of x equals x to the third minus 1, f inverse of x is the cube root of x plus 1. Now here's just another reminder that the negative 1 in this notation is not a negative exponent. The symbol f inverse of x represents the inverse function, not the reciprocal of the f function. Now here's example 4, and we're going to start off pretty easy. It says find the inverse of each function that is 1 to 1. Remember, a function cannot have an inverse function unless that function is 1 to 1. So first, let's look at this function and see if we think it's 1 to 1 or not. And remember, 1 to 1 means that the y's don't repeat. But here I see that there are two different x values that produce a y value of 2. So f, although it is a function, is not 1 to 1, and therefore its inverse would not be a function. Let's look at part B. G is 3, 1, 0, 2, 2, 3, and 4, 0. I see that no x values repeat, and I also see that no y values repeat. So G is 1 to 1, and it will have an inverse function. And to find its inverse function, all we need to do is reverse the x's and y's. So the inverse function will be 1, 3, 2, 0, 3, 2, and 0, 4. And notice that this inverse is a function itself. Now, just as we can find the inverse of a set of ordered pairs by exchanging the x and y values, we can find the inverse of a function defined by an equation the same way. For a function that is 1 to 1, we can find the inverse function using the following method. If necessary, replace f of x with y first, and then exchange the x's and y's. At that point, you have an inverse, but you don't have it solved yet where you can write it with function notation. So after you exchange the x's and y's, solve for y, and then replace the y with the f inverse label. So step 1 is what really accomplishes the inverse, but steps 2 and 3 are what make it look like an inverse and make it recognizable as the inverse of another specific function. Now we always want to be mindful of the domain and the range of the functions that we're working with. So remember that the domain is all of the x values in our function, and the range is all of the y values in our function. If an inverse function does nothing more than reverse the x's and y's, then the domain of our function f is going to have to be the range of our inverse function. And the range of our function f is going to have to be the domain of our inverse function. You see that an inverse function simply reverses the input and the output. So in example 5, let's decide whether each equation defines a one-to-one function, and if it does, then we'll find the inverse. Okay, here is f of x equals 2x plus 5. Well, I know that this graph's a line, and I know that since it has a positive slope, it's increasing on its entire domain, so I can say that it's one-to-one. Now, to find the inverse, I will replace the f of x with y, and now step 1 is swap the x's and y's, and step 2 is solve for y. So I'll need to get this plus 5 onto the other side and divide both sides by 2. And now my inverse is solved for y, but I want to give it an inverse label. So now I'm going to say f inverse of x equals x minus 5 over 2. And let's look at part B. We see that this is a quadratic function, and therefore it will graph a parabola. And we know that parabolas fail the horizontal line test. So this function is not one-to-one, and therefore it will not have an inverse function. Here we have our last equation of example 5. This one says f of x equals x minus 2 to the third. The first thing we need to do is decide if this function is one-to-one, and if it is, then we will find its inverse function. Now I know this function is going to be one-to-one because I remember from previous experience that the function x to the third is one-to-one because it's increasing on its entire domain. This function's graph would be the same graph as x to the third, but it would be moved 2 units to the right. So this function is also one-to-one. Let's start finding its inverse by writing f of x as y equals x minus 2 to the third. Now we will swap the x and the y, so we'll have x equals y minus 2 to the third. And now we will solve for y. To solve for y, we'll need to eliminate this exponent of 3, so we'll do the cube root on both sides. And because this is an odd root, we do not need to insert the plus minus symbol. So now we have the third root of x equals y minus 2. And we're still trying to isolate the y, so now we will add 2 to both sides. And y equals cube root of x plus 2. So now all we have to do to finish it off is replace the y with the f inverse notation. So f inverse of x equals the cube root of x plus 2.